Welcome to your final lesson on polynomials. So in this final lesson of polynomials, we're going to go over some really important theorems. Let's start with the fundamental theorem of algebra. The fundamental theorem of algebra states a variety of things, actually. But to sum it up, it basically says that if you have a polynomial of degree n, right, as you can read here in the second sentence, if you have a polynomial of degree n, it's going to have n amount of complex zeros, all right? So stop thinking about that. N complex zeros. That means a cubic function has 3 complex zeros, a quadratic has 2 complex zeros, a linear function has 1 complex zero, a fourth degree function has 4 complex zeros. All right. Now, a little bit about complex zeros. A complex zero is one of two types of zeros. You can have a real zero, which means you're going to see it cross the x-axis. And that real zero in itself could be a rational or a nice type of number. I say nice, that's subjective, right? But we're thinking integers, whole numbers, maybe fractions, or you can have an irrational number, a non-terminating decimal, just a really ugly looking zero. But regardless, you can have a real zero, which means it crosses the x-axis. You can also have an imaginary zero, which means that there are roots to the polynomial equation, but they're not visible as x-intercepts. All right, so let's take a look at both of those, or at least how we would find all the complex zeros. Because again, if a polynomial has degree n, all right, such as x cubed, all right, then it is going to have a total of, and look at the lag on that. X cubed is going to have a total of 3 complex zeros. All right, so let's get to it with an example. No, this is lagging bad. Well, one other thing we need to know as far as theorems go is the conjugate root theorem, which means if you have a root a plus bi, you're also going to have its conjugate, a minus bi. Same with the rationals. If you have a plus the square b square root of c, you're going to have also a minus b square root of c. So conjugate, so roots really travel in pairs, all right? And we're going to see that once we look at some more concrete examples. So let's take a look at our first example. Here is x cubed minus 10x squared plus 34x minus 40. And if we're finding all of the complex roots, well, it's easy to find the real, and I call them roots. I can call them zeros as well. It's easy to find the first real one. We know, and I have it written right here, we can quickly notice that x equals 4 is a real zero. All right. Follow this up by factoring. All right. So I can determine that x minus 4 is a factor. And I'm not going to go over the method of choice that you want to, but you need to find the quadratic factor. You can do this through long division, synthetic division, the box. Either way, I've determined that this is the factored form, and it is correct because my graphs are equivalent. And at this point, if I want to find the remaining roots, I would use the quadratic formula. All right, quadratic formula, also a Math 2 topic. So if you correctly use the quadratic formula for this problem, you'll find that the remaining roots are 3 plus or minus I. So there you have it. A cubic function, third degree, has 3 complex roots. Of those 3, one of them was a real root, a real zero, and that's x equals 4. Where are the other 2 zeros? Well, they're complex zeros. They're these, in this case, they're imaginary. One of them is 3 plus I, one of them is 3 minus I. And let's get a quick visual on how the quadratic formula would work out for that. And so anyway, choppy video, I apologize. Here's the use of the quadratic formula. So to find the remaining zeros, I basically need to use a equals 1, b equals -6, c equals 10. Substitute this into the quadratic formula, which is opposite b plus or minus square root of b squared minus 4ac, all divided by 2a. And I will arrive at 3 plus or minus I. And in Desmos, I just used plus, but it's really 3 plus or minus. So those are your remaining 2 zeros. They are imaginary zeros, 2 imaginary zeros, 1 real zero, and you have 3 total complex zeros.